is my today's electromagnetic field session. Today I am going to tell about the Faraday's law and the time varying field. Myself Dr. Sayanti Chatterjee, Associate Professor of Department of Electrical and Electronics Engineering in Hyderabad Institute of Aeronautical Engineering, Hyderabad. So, this is the field, time varying field. In this topic, we will discuss about the Faraday's law of electromagnetic induction and note the nature of EMF induced in the coil for fixed and variable fields. Number 2, list out the differential and integral form of Maxwell's equation for time varying field. Number 3, we will discuss the Maxwell's equation to produce a wave equation for the free space insulators and conductors. So, first question, we will start what is field. When we are in the very first class of this session, we have discussed what is field. A field is a function that specifies a quantity everywhere in a region or a space. A field is a spatial distribution of a quantity. In general, it can be either scalar or vector in nature. We can see that this is the transmitter and this is our mobile. This is our daily life things. There is one transmitter and this is our mobile phone. So the mobile phone, the electromagnetic fields are coming, the sounds are coming through the electromagnetic field from the transmitter to the receiver. So this mobile is the receiver. So this area is known as the field. And generally field means the area where we can experience some force. So what are the types of electromagnetic field? Electromagnetic field is basically three types. One is electric field, which is due to the electric charge. Another one is the magnetic field. What is the meaning of magnetic field? Magnetic field means if we keep one permanent magnet, we can experience some force. This is the magnetic field. And another one is the electromagnetic field. What is the meaning of electromagnetic field? If we give the electricity to any soft iron, it will change into magnet. This is the basic working principle of any type of motor, generator, transformer or any electrical appliances. And electrical field is two types. One is time independent. If the source is DC or the one directional current, we can tell this is a time independent field. And what is the time varying field? If the source is AC, the current is changing, the flux is always changing with time, we can tell it as the time varying field. So, how the time varying field? Today our main discussion topic is the time varying field. Our main concentration is on the time varying field. So, what is the time varying field? Time varying fields are produced due to the accelerated charges or time varying current. If the currents are changing, say if this is the AC current, you can see this green one is the AC current, or this is dotted because current is nothing but the flow of charges. So if the charges flowing is in the this direction, it will produce some time varying currents. A time varying field is produced by a time varying magnetic field and time varying electric field. And time varying magnetic field is produced by a time varying electric field. So time varying electric field is produced by a time varying magnetic field and time varying magnetic field is produced by the time varying electric field. So we can understand that the both fields are interrelated. That's why it is known as the electromagnetic field. The first concept was experimentally introduced by the Michael Faraday and it is theoretically proved by the James Clerk Maxwell, and these two persons are known as the father of the electromagnetism or father of electricity. So, when there is a change of flux, what will happen? a changing magnetic field intensity will induce an electromotive force. Induced an electromotive force when there is a change in the magnetic field, that is magnetic field intensity, it will induce an electromotive force. Electromotive force is always in the open circuit. When it is a closed circuit, we will tell it is at the voltage. So you can see this is the changing electromagnetic field, and as a result what will happen? In a closed circuit, a changing magnetic field will produce a electric current. We can see it can produce an electric current. So what is the Faraday's first law? So about this electromagnetic field, Michael Faraday has given his first law. What is the his law? His law is, what is the law? Any change in magnetic field of a coil of wire will cause an EMF to be induced in the coil. If there is a change in a magnetic field, or rather we can tell in an electromagnetic field of a coil, it will cause an EMF to induced in it. And this EMF of this induced is called and the induced EMF. And if the conductor circuit is closed, the current will circulate. Already we have discussed in the previous slide, will circulate through the circuit, and this current is called the induced current. So if, as this is the rate of change of current is there, it will induce some EMF. So how we can change the magnetic field or electromagnetic field? First of all, we can change it by moving the magnet towards, means if this is the field, if we bring the magnet near or far, the intensity will change. As we know, intensity depends on the length. Number 2, by moving the coil into or out of the magnetic field. If this is the coil and this is the field, if we take it out or if we take it in, simultaneously we can change the magnetic field cutting in it. What is the third? Third one is by changing the area of the coil placed in the magnetic field. If we are changing the coil, means if this is the magnet, two magnets are here, north and south. If we change the north pole here and south pole here, if we change the position of the magnet, it will change the cutting of the magnetic flux. And if we rotate the coil relative to the magnetic field or relative to the magnet, this is basically the working principle of any generator. If we move the coils, we can change the magnet. What is the Faraday's second law? Faraday's second law states that the magnitude of EMF induced in the coil is equal to the rate of change of flux that linkage with the coil. So EMF is directly proportional to the rate of change of flux d phi dt. EMF is directly proportional to the rate of change of flux, or we can tell minus d phi dt. And the flux linkage of the coil is the product of number of turns of the coil. E is directly proportional to the n d phi dt, number of turns of the coil and the flux associated with the coil. So E is equals to n d phi dt. And what is the third one? Third one is the Lenz law. Though Lenz law is the another law of the electromagnetic induction, but we can assume as it is the important and the third law of the Faraday's law. What does the Lenz law tells? Lenz law tells that, so what is the Lenz law tells? Lenz law states that the cause opposes every cause of producing it. So if we in the electromagnetic direction, we can tell the direction of the induced EMF is such that it will oppose the change in magnetic flux that causes the EMF. So the direction of the induced EMF which drives the current around the loop, if this is the north pole and south pole, and the direction of this rotation will be such that it will oppose its cause. So what Faraday did the experiment? He took an electromagnet and he keep it in a and connected a plain simple coil in a magnet. So Michael Faraday first discovered this Faraday's law in the year of 1831, and after almost 200 years, it is still now in our action. It is the base of any type of electrical engineering. So he moves the magnet and he checks there is some induced current in the coil, and therefore he measures there is a current flow in the coil. And when he reverses the direction of this current, what will happen? When he change the direction of the north pole and south pole, the current also reverses. Means he took the magnet and reversed it. And whenever he reversed the south pole to north pole, what happened? The direction of the current has been changed. The green one is showing the direction of the current when he reversed the north pole and south pole. And moving the loop. Now, second, what he did is he keep the magnet constant, and he is changing the loop. He is rotating the loop. And in this case also, as there is a rate of change of flux is changing, there is a flow of current again. This induced current is set up by an induced EMF. It set up an induced EMF. Again, what he did, he then takes the two coil and he changing the current in the right-handed coil. Now, he removed the permanent magnet. What he did, he takes some coils, one coil and two coils, and he is giving the current in the right-hand side coils. He is giving the current in the right-hand side coil, and there is a rate of change of current in it. And he saw there is some flux EMF is induced in the left hand coil. The induced current does not depend on the size of the coil in the right hand. It doesn't depend on the size of the coil of the right hand. And the induced current depends on the di by dt. Because we know that due to the change in current, flux will change. So di dt is same with the d phi by dt. So when there is a rate of change of current, we have just discussed about the inductance in the previous lecture. So if we change the di by dt, what will happen? It will induce some EMF. Next is and on that we will get the Maxwell's fourth equation, and Maxwell's fourth equation is also known as the Faraday's, I forgot to write, Faraday's law in vector form. So the question may come in the two language. What is the Maxwell's fourth equation, or write the Faraday's law in vector form. So how to got this? We know from the Gauss law, phi is equal to B into ds, and this is a surface integral. What is the formula? The flux enclosed in a closed path depends on the flux density and the surface area. Hence, the EMF induced is already we have discussed from the Faraday's law. E is equal to minus d phi by dt. When we are assuming a number of turns equals to 1. Now in the place of phi, we are putting the value integration of B ds. So what we will get then? We also know that the electrical potential EMF E is equal to E dot dl. We know V is equal to E, dV is equal to E dot dl. Already we have discussed it also many times. As voltage and EMF is same, if it is open circuit, we will call it EMF. If it is closed circuit, we call it voltage. So what is E? E is equal to what is V? Integration of E dot dl. So E is equal to integration of E dot dl. So in the previous section, we got E is equal to dB ds by dt. Here we got integration of E dot dl. Both is equal to E. So if we apply the Stokes theorem here, E dot dl, we are changing the range. So E dot dl is equal to grad cross E into ds. From dl we are changing to ds. That's why we are using the Stokes theorem. So grad cross E into dl. So here is dl. So if we equate these two equations, what we will get? We will get grad cross E ds equals to integration of dB ds by dt. So both side is ds. If we just equate this equation, we will get grad cross E is equal to minus dB by dt. So this equation is known as the Maxwell's equation or vector form of Faraday's law. Next we will discuss the types of EMF induced in the coil. For electrical engineering, EMF is the one of the main important thing, and for any motor and generator, transformer or any type of electrical appliances, EMF is one of the important thing. So EMF is induced due to the rate of change of flux. EMF is basically two types. One is called the statically changing EMF. Another one is called the dynamically changing EMF. So what is the EMF? So we got the induced EMF from the Faraday's law. E is equal to minus N d phi by dt. Now phi can be changed basically two types. One point is we are keeping the field constant. We are changing the coils. This is the basic principle of any motor or generator or any electrical machines. We keep the flux constant and we are moving the rotor. Rotor means we are moving the coils. This is the one case of changing the flux. What is the another method? We are keeping the conductors constant and we are changing or rotating the flux. So this is the another method for cutting the rate of change of flux. And depending on this, the EMF is basically two types. One is called the statically changing. Another one is called the dynamically changing. So what is statically changing? Conductors are stationary and flux is variable. We are keeping the conductors or rotor fixed and we are changing the flux. This is the example of a transformer. What is the another one? Another one is the dynamically changing. What is the meaning of dynamically? Dynamically changing means conductors are rotating but flux is constant. So we got two types of EMF, statically changing EMF and dynamically changing EMF. So first we will discuss about the dynamically induced EMF or motional EMF. So as we discussed earlier, in order to generate a dynamically induced EMF, the magnetic field must be kept constant or stationary and coils and conductors are moving. Think about a DC motor. This is a north pole and this is a south pole. So there are some constant electric field is there. Now we are keeping one rotor or armature here, and using the prime mover, we are rotating it using a prime mover with the shaft. We are rotating the armature. What will happen? The rate of change of flux cutting will change and it will induce the EMF. So, if the aforementioned processes are followed, the conductor cuts across the magnetic field and the EMF is induced in the coil. Already we have discussed this thing. And therefore the potential induced can be written as E is equal to EBLV sin theta. What are the examples? We told already. Motors, generators. These are the example of the dynamically induced EMF. So how we are getting the value? Think about any motor or anything, north pole and south pole, and these are the arrows are the lines of flux. This is the moving coil. This is the moving coil, and we are moving this coil in the magnetic field. So what is the flux? QB. QB is equal to B into A. B into A. Total flux into A means cross-sectional area. We are assuming this is a rectangular shape. The rotor is a rectangular shape whose width is D and length is X. So what is A? A is equal to D into X. So what is the flux? B dx. Now what is the force? Force is equal to, this is from the Lorentz force, Q is equal to V cross V. What is force? Force in a time Q is equal to V, the velocity of this rotating coil, cross B. B means flux density. So if we divide F by Q, what is F by Q? F by Q is equal to V cross B. F by Q is equal to V cross B. So what is F by Q? We know from the unit 1, the F by Q is nothing but the field intensity. So what is the field intensity? V cross B. So V cross B means we can write it as the VB or VV sin theta. V cross B can be written as the VB sin theta from the cross product. Now, what is the relation between V and E? V is equal to E intensity into L. What is this B? This B is the potential. We know from the unit 1, the potential is equal to field intensity E into length. Now, the potential and EMF is the same thing. As I told earlier, EMF is for the open circuit, voltage is equal to the closed circuit. So, we can write it with the small e or EMF. So, if we put the value, we get E is equal to VBL sin theta. VBL sin theta. And when the theta is maximum? When theta is 90 degree. When the flux cutting is maximum. When theta is 90 degree. What is theta? The angle between the flux and the coil. And when it is maximum? When the angle is 90 degree. It is rotating. So, this is the flux. If this angle is 0, no flux is cutting. It is parallel. This is a coil and my hand is the flux. So, when it is parallel, no flux is cutting. Now, coil is rotating. When the coil is in the 90 degree, all flux are cutting with it. So, at this moment, theta is maximum and we got maximum value E is equal to BV into L. Now, what is statically induced EMF? Unlike the dynamical or motional EMF, this EMF is known as the transformer EMF also. So, we know transformer is a static device. So, magnetic field must be rotating and the conductor must be static. What is the thing? The conductor is static but the magnetic field is rotating in nature. So we got this value. So if conductor experience the variable flux, EMF induced in it is called as the statically induced EMF. So what is the example? Already I have told, it is the transformer. You can see this is the field and this is the loop. Now we are changing the field. The field is changing here. The black line is showing the field is changing here with an angular velocity omega. So we know that E is equal to E dl, already we know. And if we know what is E dot dl is equal to n d phi by dt from the, whose equation is this? This is the equation of the Faraday's law. So E dot dl is equal to minus n d phi dt. So what is the cause of the generation of flux? The generation of flux is nothing but the AC current. So if the EMF, if the current I is equal to Im sin omega t, then phi will be phi m sin omega t, because phi is directly proportional to I, or we can write phi is equal to Li. So phi m sin omega t. So what is E? E is equal to n phi d of phi m sin omega t dt. After integrating this, we can get n phi m omega cos omega t. And statically EMF induced is maximum when the angle omega t is equal to 0. When omega t is equal to 0, we will get the maximum value of the statically induced EMF, and the value is then n pi m into omega. Next, we will discuss about the another important thing, displacement current. What is the meaning of displacement current? As I discussed in second unit, current is basically three types. One is called the, I will write here, current is basically three types. What are the types? First one is called the drift current. What is the meaning of drift current? Drift current means if we are giving any potential or voltage, current is forced to flow. This is called the drift current. What is the another current? Another current is the motion current. When there is a flow of electrons in anywhere, current will automatically flow in the opposite direction of the flow of charge. This is called the motion current. So drift current is the forced current, but motion current is basically nothing but the natural current. If there is a flow of change of current, electrons, the current will flow in the opposite direction. And what is the other one? Last one is known as the displacement current. Displacement current is nothing but the, if any dielectric medium is connected with any source or any capacitor is connected in any source, there will be, in the ideal condition, there will be no flow of electrons through the dielectric. But in the practical case, there will be a little amount of flowing. This current is known as the displacement current. So displacement current depends on the capacitance. We can write IC is equal to C dV by dt. We know current is C dV by dt. And what is capacitance? Capacitance is epsilon A by D. What is epsilon A? Epsilon is nothing but the permittivity of the medium. It is nothing but the permittivity of the medium. Permittivity of the medium. Already we discussed this thing. So what is IC? We are just putting the value here. So IC is equal to epsilon A by D dV by dt. Now if we divide the IC by A, we will get epsilon D of dV by dt. this d is nothing, this small d, this d is nothing but the distance between the two dielectric. So we can write it epsilon dv into d by dt. So again we know dv by d means we know E into dl is equal to v. Here we can write that, we can write it as the E. So what is this? This is the IC by A is equal to DE by dt. And what is epsilon E? We know the flux density D is equal to epsilon into E. We know this. So epsilon into D, we can write D into capital D. What is capital D? This is nothing but the flux density. What is JC? JC is equal to known as the displacement current density. So displacement current density depends on the dD by dt. So this is known as the displacement current density. JC is equal to dD by dt. What is dt? The differential change in flux density. Now we will discuss about the conductor current or motion current density. So conductor current density refers to the amount of current flowing on the surface of a conductor in a time t. If there is a general conductor, there is a flow of charges, and this is called as the surface current. So in this equation you can see there is any conductor means there is some IR and IC. So what is the current I? I has two parts. One is IR. In yellow you can see, and another one is the IC. It is drawn in this orange color. So I is the total current, IR is the current through the resistance, and IC is the current through the capacitance. So we are dividing it using the KCL. We are dividing it by area A. So I by A is equal to IR by A plus IC by A. So we can write I by A is equal to J, total flux density, is equal to JR. What is JR? Conductor current density, and JC already we have discussed, displacement current density. Next, last part is the Maxwell's equation in time varying field. What is the Maxwell's equation in the time varying field? In the time varying field, we can write that E equals to E naught cos omega t. So EMF or intensity is equal to E naught cos omega t. We can write that E naught j omega t. So if we got the intensity value, what is the relation? E and D, D equals to epsilon into E. So epsilon is a constant. So if E is a cosine graph, D should have the same property. So D, flux density D is equal to D naught E j omega t. So what is D by dt? What is D by dt? It is nothing but the JC or displacement current. So displacement current we can write as D naught omega e to the power j omega t. So it is j omega d naught. So if we get this is the what is D? D is nothing but the electric flux density. So if we use the same formula in the magnetic flux, we will get dB by dt is equal to j omega B or B naught. So this is for the, or B is the magnetic flux density. This is nothing but the magnetic flux density. So already we got from the Vector's law of, already we discussed about the vector law of the Faraday or Maxwell's fourth equation, grad cross E is equal to minus dB by dt. And what is the value of minus dB by dt? J omega B naught. So grad cross E, the grad cross E is equal to J omega B, where E is the field intensity. We are not taking the direction. So already we got that we are not taking the direction, or minus sign, direction is not taking. We are not taking the direction. So similarly, if we use this one J omega B, we can, what is B? Here we can take the direction also. Minus, if we are taking the direction, we can write J omega B is equal to mu H. And we can also know that the grad cross H, if we are taking about the H is nothing but the field intensity. We have discussed before also. Grad cross H is equal to J plus D by dt, means total current density, by D by dt means it is nothing but the displacement current density. So what is J? J is equals to sigma into E. What is sigma? Sigma is nothing but the conductivity of the medium. So already we know grad cross H is equal to J plus D plus dt. Or we can write from the previous slide. Okay. So what is this? J omega D naught is equal to epsilon E. So if we take the E constant, we will get grad cross H is equal to E sigma plus J omega epsilon, where epsilon is the permittivity of the medium. So we got the relation grad cross H is equal to E sigma plus J omega epsilon. This is the Maxwell's equation in the time varying field. If we want to write it in the integral form, we can write grad cross H is equal to J plus D plus dt. Already we got. So we got up to this proof that J is equal to epsilon into E plus J omega D naught. We are just putting the value. So what is grad cross H? Grad cross H into dl. If we calculate the grad cross H into dl, if we or we can multiply ds both side. Grad cross H ds is equal to E sigma plus J omega epsilon into ds. We are multiplying ds both side. If we do the integration both side, what will happen? Grad cross H ds, we can use the Stokes theorem. Here. Stokes theorem means dl will be changed in the one more or one less. If we remove the grad, we will get H dot dl is equal to, we can write sigma plus J omega E, all are constant, integration of field E ds. This is the integral form of the Faraday's EMF equation. This is known as the integral form of the Faraday's EMF equation. So if we write the Maxwell's law in a glance, we can see there are the equation grad cross E is equal to minus del B by delta T. Already we have discussed in the chapter that the grad cross E is equal to del B by del T. And we can also use this in the integral form, that the E dot dl is equal to minus del B by del T into ds into s. We can prove this also. Grad cross E ds equals to, we can write minus delta B by delta T ds. Now if we integrate both sides and we are applying the Stokes theorem, and we want to remove the grad using the Stokes theorem, means it will be one lower from surface to line. So it will be E dot dl is equals to the minus of del V by del T ds. So we got this formula, and why it is a line? Because in the Faraday's law, if there is any closed path, current will flow. So closed integration of E dot dl is equal to minus del V by del T s ds. So this is the Faraday's law. Again, already we have discussed this equation, grad cross H is equal to J plus del D by del T. Already we have discussed these two equations. This is known as the Ampere circuital law in a time varying field. This is the Ampere circuital law for the time varying field. Next, grad dot D is equal to rho B. So if similarly we can change it according to the Stokes theorem, that it is the Gauss law, and grad dot B equals to 0. If grad dot B equals to 0, B dot ds is equal to also 0. So this is the Maxwell's first equation. We got it from the unit 1 and it is from the unit 3. We have done this proof in the previous two chapters, and it's both two are in the unit 5 we have discussed. So these are the main important. These four are known as the differential form, as there is no integration sign, or it is known as the point form. And these are the integral form of the Maxwell's law. So this is the today's class, and thank you.
Like, share and subscribe. Hit the bell icon for more updates.